In this example, the particle P, its path is given in terms of its x and y components. Here, x and y are explicitly given as a function of time. So in order to get the time derivatives of x and y, it's a fairly straightforward operation of just doing the differentiation in an explicit way on x and y. So let's do that here. We're given that x is equal to t squared minus 4t plus 20. So therefore we can say that x dot is equal to 2t minus 4, and y dot is equal to 3 times 2 times cosine 2t. So that gives us the components that go into velocity. So the velocity vector, whatever number we get there for x dot, multiplies I, and the number we get from y dot, that multiplies it times j, and that's it. Take one more time derivative, so we get x double dot here is equal to 2. Y double dot, we have a 6 in front of the cosine, so we multiply that by minus 2, because we're taking a time derivative of cosine 2t. So that gives us minus 6 times 2. Sine 2t. So from that, we have the components that go into the acceleration vector. So A is equal to x double dot I plus y double dot j. So again, putting in our time here of 3 seconds in for those expressions for x dot, y dot, x double dot, and y double dot, we have v and a. The second thing we're asked to find is the angle that exists between v and a. So again, these components of v and a are known in terms of x and y. We'll allow you to put the numbers in there for x dot and y dot, but the v vector is going to be looking something like this, and the a vector will be like this. So the question that's being asked then is, what is this angle of theta that exists between v and a? Well, the easiest way, I think, to find the angle is to take the dot product. Because if we take the dot product of v and a, what we have is, by definition, it's the magnitude of v times the magnitude of a times cosine of the angle that exists between those two. So using this, we can get that the cosine of that angle that we're trying to find is the dot product of v and a divided by the magnitude of each one. As that. So v again is x dot I plus y dot j. Magnitude of a, that's x double dot squared plus y double dot squared, square root. Magnitude of v, that's x dot squared plus y dot squared. Take a square root of that. And it looks like I quit too soon there on the top. That's v, and then dot that with a. So that's x double dot I plus y double dot j. So we take the dot product of those two vectors there on the top, we multiply together the x components, multiply the y components, and add those together. And again, we divide by the magnitude of each one, so that's this. So in order to complete this, we need to put in the value of t into the expressions for x dot, y dot, x double dot, y double dot, plug those into that expression, and then take the inverse cosine of that, and that gives us the angle that we need between V and A. So if we go back over what we have here, we have a problem where the x and y components are explicitly given to us in terms of time, so that makes the Cartesian expression for V and A very nice, just taking time derivatives of x and y. That gives us the components for V and A. And lastly, the angle between these two vectors, there's a number of ways that you could do it. You could use a little bit of trig and maybe find the angle between V and the x-axis and A and the x-axis, and then subtract those two. But I think the most straightforward way here, and we need to get used to using vector operations, and that is to take the dot product of the vector for V, the vector for A, and from that we get our expression that's shown here for the cosine of that angle.